today's theorem.
Yeah. So hello everyone. Today we are here to listen to this lecture series organized by CHEP on open quantum systems and quantum mechanics, quantum field theory, and holography. So our speaker is Aranya Bhattacharya. He is a postdoc here. He joined in 2021, and so yeah.
Okay, thank you. Shall we talking about open quantum systems, mostly in quantum mechanics, but towards the end I'll also talk about bit in CHEP-th and holography. So to begin with, to motivate it, what I'd like to say is basically, although we mostly deal with quantum mechanical theories or whatever mechanisms or machineries that we use are particular for closed systems or isolated systems. For example, the very basic thing that we use is a unitary evolution, but it is also an effect of basically this closed system thing. But, in the most pragmatic sense, whatever experiment we do or whatever thing we observe from experiments, the results are supposed to show us some kind of non-unitarity because of our this closed system assumption is an approximation or an idealization. So if we really want to when we are doing some experiment and taking data, basically it is very hard to prepare some experimental setup which doesn't have any interaction with the environment. And if we have any environmental interaction, then, and given we don't have, let's say, the exact knowledge of how our experimental setup is interacting with the environment, then the data is supposed to show us some non-unitarity or signatures of non-unitarity due to this interaction. And open quantum systems are one way to study such behaviors of a system when we, let's say, don't know everything about the environment, but we don't know everything about the environment, but we want to be able to pick up certain, at least have an idea of how much it is interacting with the environment or what kind of interaction it is by looking, let's say, the set of data that is available to us. And of course, there is supposed to be some signature of non-unitarity in the data, and we want to pick up those signatures to be able to say something like how the interaction is, how strongly the system is coupled to the environment, and so on. So, yeah. So ideally, another thing would be that if our environment is, let's say, the rest of the universe or the lab, and and at the same time the coupling between the environment and the system is very, very small, then one would expect to, let's say, at least get back some results which are expected from closed system or isolated system results. So in that limit, it should give us isolated system results. So the general idea is to form or to study a set of equations or a way of evolution through which we can generalize this thing. So we can study both a system interacting with the environment as well as an isolated system. So we can always, in this generalized setup, one can put, let's say, some interaction or some non-Hermitian term that would arise when studying this due to the interaction with the environment. We can put those non-Hermitian couplings to zero to get back our isolated or closed system results. So from another perspective, it is also interesting. For example, we know that, for example, the recent unitarity or the pH curve resolution of the black holes that was done in the last couple of years was again done in a way such that black holes plus the rest of the universe or the radiation, the combination of these two have this unitarity or the page curve, show us the page curve. But the black hole by itself is not expected to be a unitary system. So if, it is also coupled to this environment or the rest of the universe. So it is also makes sense to treat these black holes as some kind of open systems interacting to the rest of the universe or such a thing. And so this kind of study can possibly also teach us about black hole dynamics of such things. So with this, another point is final point would be motivation would be that when we say that, let's say in this era of quantum computation, people often say that quantum computers are more efficient or advantageous in implementing a task in comparison to a classical computer. But most of these statements come from a closed system perspective. So, for example, in terms of quantum information processing, when one makes the statement that quantum procedures are advantageous over classical computation or task implementation, many of them originate from a closed system idea. So what would we need to indeed re-scrutinize this thing from open system perspective as well? If a system is interacting with the environment and we have access over only the system part, or some little part of again some components of system through which it is basically interacting with the environment, but we don't necessarily know everything about the environment. So yeah, my plan would be today I will mostly talk about this. It will be a revision of the closed system things. For example, evolution, states, and what does measurement mean? For example, measurement we know is a non-unitary operation because this projection operators that we deal with it collapses our states. For example, certain non-unitary examples of non-unitary procedures are like measurement, and also when we, for example, while dealing with entanglement entropy and stuff, we very usually take this partial trace operator and get a reduced density matrix. This taking partial trace is also a non-unitary operation, and so I'll try to discuss these things today. And essentially, we would like to get to study a system density matrix taken after derived after taking partial trace from the full system. And when we study this evolution of the system density matrix, we would like to be able to address all kind of unitary as well as non-unitary procedures that are involved in quantum mechanics. For example, measurement or something that is called non-selective measurements that I'll talk about. Then this open system dynamics where non-unitary effects come in. So all of this we would like to see a closed form expression or some expressions which can deal with both unitary dynamics as well as measurement and non-unitary dynamics. So yeah, I'd also like to say that please ask questions whenever you feel.
So when you say that it is coupled to the environment, do you have a similar thing in statistical mechanics when the system is also coupled to a heat, the thermal bath? Aren't these analogous somehow?
You can, yeah. Basically, everything that we will be talking about, for example, there is something called this Markovian and non-Markovian limits of this open quantum systems. Those are again related to this stochastic properties and statistical properties of the system. So indeed, you can talk about canonical ensemble, grand canonical ensemble, and so on. Whenever you study a system, for example, we know the whole quantum mechanics is, so to say, a study of statistical systems, because we take ensembles to get to a pure state, and if you prepare identical copies of your quantum state in principle, and then whatever measurements you make from that, you try to talk about how the what is your state. Now in some cases you are able to definitely say what your state is if all the elements of the ensemble gives you similar results, but in some cases it can be a probabilistic mixture of different things. For example, where we talk about mixed states. Okay, so start with We know that a quantum state will typically represent it by vectors in Hilbert space. And this linear vector space the elements of this vector space closed under addition and scalar multiplication. Then there are all things you know, for example, identity exists, etc. Next thing is we talk about linear independence of these vectors. So a set of vectors, let's say phi are said to be linearly independent if this implies all CIs are zero. And in fact, this linear independence also gives us the dimension of the space. Dimension of the linear vector space is basically the maximum number of linearly independent vectors. And we say that also form a basis. How do we form the basis? The basis is formed with the maximal set of linearly independent vectors. Of course, we to say unit vectors in the space. And so we can represent any arbitrary vector in this vector space using this basis vectors phi k and certain coefficients equal to this sum of one by state. Then it's the operators. Operators act on operators are basically mapping from this vector space, same vector space. So this take one state of this vector space to another state, and there are other properties that we know, for example, linear operators is something that satisfies this property that C1 and C2 would be complex numbers. And if let's say this dimension of this vector space is n, then typically this operator has a n cross n matrix representation. And these vectors are basically in common. So yeah, these are sort of the basic things that we talk about. Now let's revise a few things which will be again important for us going forward. So we'll now talk about the three equivalent ways to deal study quantum mechanics, which are basically the Schrodinger picture, Heisenberg picture, and the interaction picture. Yeah. So in Schrodinger picture, we know that only the states evolve, and operators do. And the state evolution is written by this equation. So this is my initial state, and this is my state at time t. And this is the unitary operator, which is basically in case of time independent Hamiltonian. We write it as e to the power minus IHT, where this is time independent. Whereas in case it is time independent, we know that we'll have to use the time ordered things, tracing series. And the equation of corresponding equation of motion is good. Now, if we study just this, deal with just evolving states, but try studying how the expectation value of an operator changes with this state evolution, we can go to Heisenberg picture. From that is a natural way to go from Schrodinger to Heisenberg picture. Let's say this is my general state, and this is some operator, the expectation value of which I am trying to study. Then this again, this is something that we have written in Schrodinger picture. But if we expand this, then this becomes and now we can again Heisenberg picture. In Heisenberg pictures, only operators change with time, or operators evolve. States do not. In that case, what will happen if you are studying Heisenberg picture? Let's concentrate on this expression. This becomes the states won't really evolve with time, so the states even at time t will remain psi 0, and then we can treat this as an evolution of operator, and let's put an 0 expression here, 0 here. Then we will write dt as right in terms of and the corresponding, let's say, also give Heisenberg function, Schrödinger. So psi h Heisenberg states are basically Schrödinger states at time and they will not change it. The corresponding equation of motion, you know that we can write it as in general we can write it where this each h is basically e to the power iht 80 to the power minus iht, but it will commute with at least for time independent Hamiltonians, it will always commute, and then you can just get rid of this h. Yeah. Finally, let us come to the interaction picture. Where both operators and states change. And basically, the way we deal with this is start with the Hamiltonian, where we explicitly know the eigenvalues and states for this 80 part, whereas this you can treat this as a perturbation. And this is a solvable Hamiltonian. Then we sort of already know what the spectral decomposition of this solvable Hamiltonian is. That means basically we are able to write this as this part, you know, and we try to the definition of, for example, interaction in picture states are basically evolution through the free Hamiltonian of the solvable Hamiltonian, but not really U03. Fiber. This SIS is the Schrödinger state at time 0 or at arbitrary times. This is
So is the u t comma 0 something? And u is a time evolution operator, right? So
yeah.
shouldn't it
Yeah,
evolve?
this is just t comma 0 if you start from 0 and so on.
Oh.
At 0. In general, you should be able to write this as t1 comma. So this is the evolution of states, and if I take, let's say, this, you can show this on the arbitrary time scale. Can show that this will come out to be into this VI, and this VI is nothing but your usual part B. And so this will be how the states evolve in interaction picture. They evolve in terms of this perturbation part, and operators, on the other hand, evolve in this way. Here, if we try writing down what the operator evolution equation will be, that is simply The operator evolves in terms of the solvable Hamiltonian, because the equation of motion seems so, and the interaction picture states evolve in terms of the interaction picture part of the part equation that we have. So these were the three pictures which we will mostly translate between each of those pictures. Some of these will come handy in what we are going to discuss, different stages. I wanted to talk about this now again. Are there any questions till now? Otherwise, I'll move forward. Okay, now let's just do a couple of definitions. So, what is a normal operator? The definition of a normal operator is simply that A dagger A is equals to A dagger. And as you can see, the Hermitian and unitary operators will be automatically normal operators. So, from this definition of normal operator, there is actually a theorem in quantum mechanics. It's called the spectral theorem. It tells us that basically more better definition of this normal operator is linear operator is normal if and only if there exists representation of this A as this kind of a sum for these are these form a orthonormal basis set. Of V, which are also eigenvectors of this operator. And this lambda is will be the corresponding eigenvalue. So with this, this is a definition of normal operator on the spectral theorem. And if we use this expansion, then it is easy to show that any Hermitian operator will have a lambda is, let's say this is Hermitian, which is Hermitian. So this lambda A will be equals to lambda star. So basically, the eigenvalue will be real, and for unitary case, they will just be some phase. This theta is belongs to. Now, this is here. Come to will be more important when we go open systems, which are measurements. Quantum measurements are described by state of this kind. Say 1 to n of measurement operators. That follow this. So there's a way to show this basically. Let's say I had a quantum state psi. If I make a measurement and always it's a denote measurement by this arrow, single arrow, and I'm measuring it through some NK operator. Let's say the simplest way to understand this, one example of this operators could be a projection operator. If I have put a detector in certain site to detect a projection, whether that projection is present or not, the state will always collapse depending on whether the answer is yes or no. So if the answer is yes, let's say if the outcome K is observed, then my collapse state will be in K psi. Of course, it has to be normalized. That's why we have to divide it with K. That this K is nothing but the norm of this in K size. Let's say all this way. And this is the sorry number no, this is the dimension of the inverse space that I talked about. And this PKs are the probability associated to each of those outcomes. K, of course, they are expected to some and if I use this expression of PK, the sum rule simply means that this is valid for arbitrary states of the Hilbert space. Any arbitrary states child for any arbitrary state, this expression should be valid. So this was the beginning statement that we made, that the definition of measurement operators is such that this comes from the probability going to 1. It's not probability. Sorry? Because you can the maximum possible different outcomes that you can get from a n-dimensional Hilbert space for any observable should be in, right? The number of eigenstates that you have. Okay, so now let's discuss explicit examples and how to relate this measurement operators to physical observables. So, second part of the measurement postulate is that every physically measurable quantity and observable can be associated. Let's say the observable or the physical observable that we are talking about is A. And again, we would write ideal or the good operators of the theory as we discussed earlier are the normal operators who have spectral decompositions of this kind. So this lambda is belong to U. This lambda is could also be thought of as the outcomes of the measurements that we will make. So basically, if these are the eigenstates of a variable A, so physical observable A, and this form a orthonormal set. Then an example of this MK operators will be, say, denoted by BA, which are simply the projectors. So we'll have n such projectors, and this indeed you can show that this properties that A dagger EA and other properties like you know that EA square is EA. And corresponding after measurement or after this projection is made, my state psi goes to psi A. This P measurement has been made. Simply A square value of P. This P is the probability. This is the this divided by this would be a phase. And then another two. The outcome is if it really detects that outcome, then the state after measurement will be this. So this PA is a special case of generalized measurement operators in case. This was just an example, but in quantum information literature, you regularly find people talking about something called positive operator value measures, POVMs. They also come from or originate from this measurement operators in case.
Question.
Yeah.
Do measurements can observe the phase?
No, it cannot really. It will always involve some arbitrary phase, but measurements can give you because this phase will always, whenever you are, this is a non-unitary measurement. Any projection operator is a non-unitary operation. So you get something, a polar state which has just a phase difference, which will be arbitrary phase. But the main point is that your outcome is this. Yes, you get an yes answer for this if you are trying to detect a state. Then again, after that, it will evolve, let's say, the usual Hamiltonian, and that will give rise to usual unitary evolution. But this phase is an arbitrary thing which should not make any difference.
So these phases contain additional information because I'm aware that these phases can actually contain information about entanglement.
Measurements. Yeah.
Because if there is superposition, then you can
phase difference becomes observable. So the same, instead of one project, if I use projectors or superposition of two projectors, and then I get a e to the power I theta 1 a1 plus e to the power I theta 2 a2. The difference between the, not sure about. Yeah, positive operator value users are basically nothing but this thing that I wrote earlier in tree diagram. I had a sum over it, but if I take individual and I can call them as positive operator value measures. And these are basically some positive operators. The positive operators, I mean, whenever I take this substitution value of these operators, I will take greater than equal to 0. Of course, from a probability perspective, you can understand it because these were giving me the probabilities associated to certain eigenstate PKs, and those probabilities can never be less than 0. These were basically PKs, the probabilities that we talked about a little while ago. And suppose we are given an arbitrary set of such positive operators, which sum over this one. To extend the measurement postulates that we discussed earlier, for these operators, one can use a for any, we could have written this operator as some phase into a positive operator, but this positive operator for a given operator will be given as a square root of a, which will turn out to be positive. If A is invertible, one can write this U as basically in terms of what we previously talked about, the primary talked about measurement operators in K. And if we are given just certain positive operator value measures EKs, then we can form these EK operators in this way. Measurement operators, corresponding measurement operators. By just taking this value into UKs, where this arbitrary phases. You can associate, just you are trying to construct measurement operators from a given set of positive operator value measures. So just because we know that this EKs can be, we can describe them as this NK dagger NKs. So if we use NK dagger NK here, we could have written those as EKs, and so given an EK, we can always form a measurement operator in this way. This is just a and this is an arbitrary phase that you can associate. So this freedom of choosing this arbitrary phase is the freedom to leave the overall phase of any state unspecified. This freedom is related to the same freedom. Any two states can be treated as the same phase if they are just different by a arbitrary phase. So now we have talked about measurements and basic quantum mechanical postulates. So finally, it's come to density matrices and the definitions of pure and mixed states, which will be very crucial for the study of open quantum systems, because especially the mixed states, we'll see that they are sort of the states describing system reduced to the state of a subsystem that always has some environment circling. Firstly, pure states. And basically, if I prepare an ensemble of my systems, of the system that I'm studying, can be system spaced in time, I mean, same system I'm studying again and again, or I can prepare identical systems, identical copies of the system that I want to study. And if I, for example, make measurements and study the probabilities associated to the different eigenstates, and I always end up finding for a given ensemble the overall probabilities to remain same for each of those systems. I can also associate this state to something called a pure state, which we are more, we have studied more in visual quantum mechanics, which are just let's say here's that there's some other square. However, there can be other states where instead of, let's say, I can divide this ensemble, or I can, there are two equivalent ways to talk about this. Let's say I have different ensembles which give me different such states with different probabilities. And say this one gives me some psi1 with probability q1, and this gives me some psi with probability q1. So in that case, if I make a measurement on this any general psi with this MK operators, I'll just find to give us some MK psi. Yeah, previously it was like P, but now there's another index associated to it. Here is just expectation value. This yeah.
This MK equals to UK.
Yeah. So if you are given, let's say, just some positive value, positive operator value measures, which sum up to which follow this equation, then what will be your corresponding measurement operators? You know that what these follow. Say if this was written in this form, then we know that MK dagger MK sum also will hold this one. So basically, if you use this polar decomposition of an operator, then this is like for a given MK, this will be like MK dagger MK. And this you can basically replace by SP case.
So I think that the basis of A, the MK.
basis of A is to have a
With eigenbasis of A.
yeah.
So that's so the EK basically knows about A.
Basically, yeah. For any when I'm saying K is associated to the outcome of a
Right. So it means that somehow it knows about the A that you're going on.
yes.
So the eigenbasis of A is what EK is going to do.
Yes.
It could be more closer than that.
Huh?
Point of is that it could be more closer than that.
So
So
what
they
is
need to actually measure a complete set.
You can so what does that mean? So complete set is the sum of one.
It's always one, but you know that is kind of. You can measure, you can choose not to measure. So then you can sum over. So EK sums over those. So EK is not just.
Oh, I see. So you mean like it could be like on some subset of the eigenstates that you're measuring. So basically, but I'm saying that the MK basically knows about the eigenstates of A. That knowledge seems kind of missing. Or at least if you're only measuring, let's say, the full A eigenbasis a node, then you're not really measuring MK. So you're saying like there is if MK spans the entire A.
I think the statement that both the same case and EK they can be much smaller. The number is little.
Right.
As long as I think the probabilities come to one.
Yeah, that will be. So the positive operator value measure as well as this measure operator.
So what is it called? Positive?
Operator value measures. Q.
So let me just try to understand this. So let's say there are some eigenstates of this A that you know there, and the NK can basically project onto that eigenbasis. That the subset of eigenbasis. Is that right?
Yeah, that you also can do. But you can also like have let's say you're measuring height and depth. You can just not use measure speed.
Do what?
Measure speed for that.
Okay.
Then you can just sum over. All possibilities of that. You can just get a probability of let us say getting an equal one. Worrying about other one. That
Yeah,
kind of
that will be a different operator. Right? So you
that's the thing. So that can make that kind of like code measurements can be described by this formula. So it doesn't have to be a full eigenvalue. But you just can give a certain operator, projection operator to a subspace.
right, but the subspace is of some operator is what I would say. Is that what you mean? I mean, maybe it could be that you can have like a commuting set, and then you can be a common eigenbasis, but it still would be an eigen, a collection of eigenstates which form the basis. This is what I'm very sure.
But that's the thing. I think that will happen if the EK is actually commuted. I think we have to be more conditions on it.
On what community is EK?
Let's say E1 comes here. Kind of thing when you asking, the EK will commute.
So I'm not necessarily saying that you have to have a commuting set. I'm just saying that there is one possibility which is you have an operator, and you're looking at some subset of bases, eigenbasis of those operators. Then EK can project on that.
In that case, EK will come.
With what? With what?
All
Oh yeah, sure, yeah, sure, yeah. You're saying that EK need not commute with each other also. So that means.
it's a more general case.
So that means that there can be some overlap in this. Basis analysis. Then what?
It means that you can kind of the statement is that like, this is a more general.
Sure.
Yeah, what you're saying is a special case. It can.
No, but I'm not understanding what is it making it more general, right? In the sense that if you have, let's say, one basis, one set of eigenbasis, like one set of basis elements, and then you have some measurement. What is it that you're saying which is more general is what I'm basically saying.
It's a bit of kind of complicated thing that you measure like some part of some quantum number, some part of some other quantum.
But then it will be multiple operations.
There's no multiple operators.
No, I'm talking about A. So here he was talking in the context of A. This operator is, if you have multiple operators, yes. I mean, then you have multiple operators.
This composition applies to each of these MKs individually.
Sure, that's fine. But the A equal to UP is what I was talking about. So you are saying A is You wrote A equal to UP, right? So that's a Polar equation of that operator A, or I talked about the Polar equation of M. Yeah.
Each of those.
So then I think that equation is slightly requires a little tweaking.
Yeah. So basically, this becomes, let's say, for each of those entities, you'll be able to say something like this.
Okay, I think I slightly understand that one.
But this M case, for example, when I talk about projection operators, that is probably what you were speaking about.
Yeah.
If we talk about M case as this projection operators only, then they will form a complete basis and so on. But they could be individual or different measurements summing over to one, just sum over those measures summing over to one. Measuring different things, not just same operator value. So this PKI is like this. If I want to again really talk about the PKs that we did for pure state kind of situation, then we will have to begin sum over I with the corresponding QIs associated to each of these cycles. So this is how we can actually into a more generalized definition of state, which we of course know. You just look at the mechanics. This is the density matrix. This is valid for any pure state as well as mixed states. In case of pure state, you just have one I somewhere, and any probabilities associated to this is just again this is just so for the positive operator value measures. So you just use this is what we also write as expectation values of operators that we usually deal with in quantum mechanics.
Can you repeat the definition of theorem? Pure states and mixed states.
Yeah, pure states is where, let's say, you have an ensemble or a identical preparation of many similar systems. You, let's say, study the probabilities associated to each of those ideal states of different observables. You always find that the probabilities give similar results. So it doesn't really, these CKs do not change for different systems. But if you had, let's say, parts of this system, parts of this ensemble, which I call, let's say, E1, E2, and so on, En, each of which give you different state, psi1 or psi n, each of these parts give you different states associated with different Q1. So this ensemble then looks like a probabilistic mixture of different pure states, classical probabilistic mixture of different pure states. And then you don't really know how to write this state as just one this kind of expansion of again states with certain probabilities, but it is a mixture of such things. So one easy way to remember pure and mixed state is that for mixed state you will just always have the density matrix representation. You can never have a cake representation or a linear vector representation. Now, what we can also show that the derivation is not going through the entire and with one Google is basically if we don't know the initial state very properly, that means on which we are making measurements, then we should sum over all possible states with, let's say, and we don't know the initial state properly, but we are trying to measure a particular uh, outcome of a particular eigenstate, say this k outcome or something. Then basically we should write this rho k as, here I wrote pki, where my state was also sort of known for a given psi I was trying to do that. But if I have a mixture of these things, then my rho k, that this pik is a conditional probability that I'm measuring k, but I don't know what the state is. It is the sum over all such pi's. And this inlet to work with this and use some probability expressions. For example, probability of I and k is equal to probability, this conditional probability into probability of k. Or another way of writing it is kr into I. But this p of i's are nothing but the QIs, the probabilities of these individual states, psi 1 to psi n. If you use these two expressions in this expansion, you'll find that this will come out to be just k. So k is, for example, k is a particular, let's say, projector or some kind of measurement that you are making. You are fixating on the over here. You are fixating on the outcome, but you don't know what your state was. For example, it could be a probabilistic mixture of this all qi psi i's. Then, without knowing that, if you try to write down this, what will be the result after measurement, then it will come out to you. You will be able to. You have to write that in terms of this conditional probabilities. With those conditional probabilities, you can show that if you massage this expression a little bit using these rules, you will be able to write this as in terms of this definition of rho, the general mixed state. That would say I do not know what rho I had, but for any rho, this will be the outcome probability that you get, of outcome densities that you get, the probabilistic mixtures that you get. That will be simply this should be.
So I got it. This Qn, so the n that you have there, is that the same thing as an Amsterdam theorem? That n in the mixed state thing?
Yeah.
So you basically, so the probability, yeah, okay. So I guess, so Q1s are really, the Q1s are the probabilities, and you're basically saying that, so you somehow,
In the example, the it's a mixture of different PO states, classical mixture of this PO states, where the sum I can, this is not just a superposition, but all of these PO states have associated probabilities, these probabilities, which are like the probabilities of PIs, but not the PKs. PKs are probabilities of outcomes after measurement. Probability of a particular, probability of observing a particular outcome. Let's say one particular eigenvalue, we are projecting towards that direction.
somehow the idea is that there is an ensemble of states, basically like, and In that ensemble, if you pick a state, the probability that it will be, let's say, psi k will be qk. That's the statement in the left side. Is that right? Is that right?
Yes, the probability of psi k will be 2.
And basically, you're guaranteed to find some. But the part I'm very confused about is that are you expected to necessarily find just one of the n states? Is that a
I
guarantee?
would say so. So basically, this is a fancy way of saying that I don't know everything about my system. So I have a lack of knowledge about my system, which will happen, for example, when I take a partial trace from a full pure state density matrix. It will have some mixture of information. If the total system was an entangled state, then what I find I will just have a description of a density matrix, which you cannot really write in terms of that density matrix. You cannot ever write as a outer product of
In terms of the density matrix, I can see that it has to be. Someone at this way of phrasing it, I'm getting it.
Yeah.
Anyway.
So if you remember that we primarily discussed about how I think in general it can be any. Although I wrote it in with again what Chetan said, I had the same thing in mind that when we write, let's say, a density matrix for a system where it has n number of eigenstates, we usually write the density matrix as some pi, some I with some over I. If you have n I spans the dimension of the inverse space. But in general, it could be if we are talking about the general classical probabilistic mixture of states. For example, you could think of this as this way, that I associated some qi probabilities and this thing in such ensembles. But if there are less than the number is less than that, I could associate some pi's to be 0. I could give some pi values to 0, probabilities of some particular, but it is definitely not a single kind. You cannot write it as a single just size.
Now we have reached close set.
Yeah.
That is from one group. Particularly you have erased like an state one. That is from one group. When you are defining close state,
Yeah.
that
I'm saying this kind of thing.
that creation is from one group.
Let's say this. When I write this, of course, I will take some ck square, which again from this definition of states, the ck square, sum over ck square is supposed to be v1. I'll get just something like this. Maybe something more than actually one.
When you are defining new state, that can be by one.
No, but this thing, you can always write this as this. But for this,
I think the point is that this way of writing is a slightly more restricted way of writing a density matrix. Because in a density matrix, you don't actually have to pick a basis, right? But when you say that, I think when you say psi1, psi2, psi n, the assumption is that you're going to pick the basis, and in that, when you look at it in a ensemble of there's an implicit choice of basis that are correct. I think that's the
Eigen basis of
exactly. Yeah, well, that's it. Yeah.
density matrix, that's our eigen basis.
Yeah. So I think that is the natural. Yeah. I think that was okay. So
yeah. this was conditional that given I k is there or given k I is there. What is the combined probability of this thing? That can be written in this form using conditional probability.
I mean, this pi is a coefficient there.
Yeah.
That is your pi. I mean, pi.
Previously, I was writing TKI, but if we don't know the initial state and we have measured something, which is also a density matrix I will get after measurement, that density matrix will have, I don't know what it is, let's say, but I know that my outcome is K. I don't know what this PI was. What it can be a mixture of different I's. So you have to consider some over different PI cases, this conditional probabilities, which are not PKIs or these PIs were more something that were better known to me. The point is that, yeah, just measurement on a density matrix will always do something. And properties we know should have unique trace for any state. It can be a pure state or a mixed state. Trace will always be 1. Then the rho diagonal equals to rho. The emission will be positive definite. Not semi-definite, but definite. So, in general, for mu belongs to this Hilbert space, this is supposed to be greater than equal to 0, but since trace rho is 1, trace rho is 1. So from this condition goes away. At least one of the eigenvectors has to be greater than 0 to make this trace rho becoming 1. So it will definitely be positive definite. And I'll just end with this finding property of density matrix, which will take and this all of this measurement operators, for example, that we talked about today, non-unitary operation, and this is something also the mixed states. Then we have this incomplete information has to do with also the fact that I have, let's say, access over a limited part of a system. It has an environment which makes it a pure state. For any mixed state, you can assume that there is a environment. If you associate that environment or couple this mixed state with that environment, then it will become a pure state, which is usually sometimes also called purification. So, but we will be interested in going forward is to study the properties or evolution of state which is mixed only, not pure state. But we will also get results that will be available or valid for pure states when we take appropriate limits. So the dynamics will be just the rho t. The key. In fact, I will start from this back. If you look at this expression carefully, then you will find that for any other operators, so we of course know that this rho is a operator in my Hilbert space because it is the outer product of this sum over outer products of different states. But for any other operator, any operator other than this density matrix, the evolution is basically you dagger t 0 ut. But if you start from this expression and form the density matrix and try to study the evolution of density matrix, you find there's this minute change, which makes the density matrix a special kind of operator, a natural definition of which. Sorry?
Both of these are negative.
Both of these are.
The first one is to produce the second one is to be.
Yeah, but what I try to mean is that if I think of my density matrix as an operator, and this operator evolution, I am trying to see the operator evolution of this density matrix. That
Density evolves only in solidity.
Yeah,
But it doesn't evolve in density.
yeah,
The evolution operators don't evolve in solidity, but they evolve in density.
yeah. That was precisely what I was going to, because this density matrix, although it is an operator, it describes your state. So the evolution of it is it represents Schrodinger evolution, not really Heisenberg evolution. So that's why this, although you consider it to be an operator, this is an special operator describing state evolution. Therefore, although this looks very similar to Heisenberg picture equation, it is actually in Schrodinger picture. Whereas this is in Heisenberg picture. And the dynamical equation, if we write down, it will be this. Which is again exactly similar to the Heisenberg evolution equation, but since it is the same, you can see this minus sign here, which shows that this is a Schrodinger evolution of a density matrix, describing a state. And this equation is known as using one yeah. Are these two things equal, which is probability identity? That you minus yes. Are these two things equal? These two is because this is I and K. This is a I mean, first line just probability I and the second line just no, this is like probability of I when you know K, yeah. And this is probability of K when you know. And when you sum over K, then the result is probability. The sum over these things, for example, if you sum over this Pi, that will give you one. Individually, the sums will give you one. But these two things, for example, are not equal. They don't mean the same thing. What you are, again, this has to do with the knowledge that you have. If you have knowledge about the outcome and you don't know what precise state you had, on the other hand, you could have a situation where you know what precise state you are trying to measure, but you could keep changing your outcome. And if you try looking at outcomes of different K eigenvectors, try building out the probabilities from there. Yeah.
So these EKs are basically generalized projection operators. That's the reason I think we use generalized are basically projectors onto the full basis. Somehow once you define this EK in terms of trace row EK, it kind of makes a little bit more sense.
So yeah, it is. It is done in a way so that you can relate the measurement operators to certain observables in your claim. Yeah. Now, if it is the projection operators, it is very easy to relate to certain operator in your theory just by through the values. If not, it is a more general operator, the measurement operator. Somehow is a more general operator, not just a projection operator. Then, if you want to associate that measurement to certain observable, that will be the observable.
So in a sense, this construction is sort of what justifies it. Right?
Yes. So, this construction
certainly is one where starting from the PK and getting to the PK at the end.
Yeah.
I think,
yeah. So you can think of it as making the CK as a valid observable. So next day we will basically discuss how composite systems are described and how basically this partial trace, and finally we will talk about the consistent evolution. Operators. What we will see will be interesting is this non-unitary operation, this MK daggers, we will be able to see this kind of evolution as well. The measurement, non-selective measurements on a Klaus operator evolution of state density matrix, the generic formula that we have, will have that will be valid for this kind of measurement operators as well. Yeah, I mean, I have sort of mixed up 3-4 references. There are many good textbooks on open quantum systems, 2 or 3 textbooks. There are a couple of very good reviews on open quantum systems available on archive and so on. I'll try to, by the next time we meet, I will try to make a list of them.